Eclipse Architecture. Here you can see Eclipse platform architecture. Eclipse is an integrated development environment IDE used in computer programming. It contains a base workspace and an extensible plugin system for customizing the environment. It is the second most popular IDE for Java development and until 2016 was the most popular. Eclipse is written mostly in Java and its primary use is for developing Java applications, but it may also be used to develop applications in other programming languages via plugins including Ada, AB, AP, C, C++, C#, Clojure, Cobol, D, Erlang, Fortran, Groovy, Haskell, JavaScript, Julia, Lasso, Lua, Natural, Perl, PHP, Prolog, Python, R, Ruby, including Ruby on Rails framework, Rust, Scala, and Scheme. It can also be used to develop documents with LaTeX via a TextClips plugin and packages for the software Mathematica. Development environments include the Eclipse Java Development Tools JDT for Java and Scala, Eclipse CDT for C, C++, and Eclipse PDT for PHP, among others. Now we are focusing on Workbench. The Workbench provides the user interface structure for Eclipse. The purpose of the Workbench is to facilitate the seamless integration of tools. These tools contribute to extension points defined by the Workbench. The Workbench is responsible for the presentation and coordination of the user interface. The tools metaphor is not specific to development tools but can apply equally well to arbitrary applications. Note that the Workbench is sometimes called the generic Workbench to distinguish it from its instantiation in the Eclipse IDE, where it is called the IDE Workbench. Unlike SWT and JFace, which are both general-purpose UI toolkits, the Workbench provides the UI personality of the Eclipse platform and supplies the structures in which tools interact with the user. Because of this central and defining role, the Workbench is synonymous with the Eclipse platform UI as a whole, and with the main window the user sees when the platform is running. The Workbench API is dependent on the SWT API and to a lesser extent on the JFace API. The Workbench implementation is built using both SWT and JFace. Java AWT and Swing are not used. Here you can see ownerships of views and editors. The Workbench contains one or more Workbench windows, each of which contains 0 or more Workbench pages. The Workbench window supplies the trim widgets, and the Workbench page supplies the window contents. In theory, the Workbench window can contain any number of pages, but in practice, there is never more than one page in a window. Views and editors are owned by page. Through a view factory and editor manager respectively. Editor manager stores the list of editors and their shared resources, and view factory stores a reference counted list of views. The Workbench works in terms of editor references and view references, and in situations where the distinction between editors and views is not important, we will simply use the term part. The implementation of the part, typically an iEditor part or iView part, is created lazily when it is first needed. A part reference exists for every tab, but the implementation is only created the first time it becomes visible. The page owns a set of perspectives. Perspectives contains a layout and information about what action sets to enable. Although perspectives appears to contain views and the editor area, they only own a layout. Page itself maintains a reference count for how many perspectives are using each view, and has complete ownership of the parts and editor area. Not shown in this figure are classes perspective helper and editor area helper. Workbench contains Workbench windows. Workbench window contains Workbench pages, and Workbench page contain editor manager, a view factory, and perspectives. Editor manager contains editor references, and editor reference contains 0 or 1 iEditor part. View factory contains reference counts, and reference count is connected to view reference. View reference contains 0 or 1 iView part. Perspective is connected to reference count, and increments are passed from perspective to reference count. Here you can see Workbench objects and what they look like. The Workbench contains one or more Workbench windows. Each of which contains 0 or more Workbench pages. Workbench window supplies the trim widgets, and the Workbench page supplies the window contents. In theory, a Workbench window can contain any number of pages, but in practice, there is never more than one page in a window. View and editors are owned by the page. through a view factory and editor manager respectively. Editor manager stores the list of editors and their shared resources, and view factory stores a reference counted list in a list of views. Workbench works in terms of editor references and view references, and in this art and in situations where the distinction between editors and views are not important, and we will simply use the term part. The implementation of the part, typically iEditor part or iView part, is created lazily when it is first needed. As shown in this figure, a part reference exists for every tab, but the implementation is only created the first time it becomes visible. The page owns a set of perspectives. Perspectives contains a layout and information about what action sets to enable. Although perspective appears to contain views, an editor area, they only own a layout. Page itself contains a reference count for how many perspectives are using each view, and has complete ownership of the parts and editor area. Not shown in this here are the classes perspective helper and editor area helper. As an example, we can consider a workbench class. The workbench class represents the top of the Eclipse user interface. Its primary responsibility is the management of workbench windows, dialogues, wizards, and other workbench related windows. Note that any code that is run during the creation of a workbench instance should not require to access to the display. This class is in package org.eclipse.e4.ui.internal. As an example 2, setting workbench preferences lets you set up the workbench to suit your needs. Open the step 1. Open the workbench and click Tools, Preferences. The Preferences dialog appears. The step 2. Set the preferences you want to use for your workbench sessions, and click OK to save changes and dismiss the dialog, or click Apply to apply changes only. Step 3. Optional. Click the Restore Default button to restore dialog settings for the currently displayed preferences to their default values. Your workbench preferences are set. We can consider this as an error example. Problems occurred when invoking code from plugin org.eclipse.ui.workbench. If you want to start your Eclipse, choose your workbench to load and then Eclipse stops. You probably have a workbench error. To fix this, follow the steps. Go to workspaces, then your workspace, then .metadata, then .plugins. Find the folder org.eclipse.e4.workbench, delete it, restart Eclipse. Now the problem is fixed and Eclipse will start again, but be aware that to a workspace layout will be back to default. This error can be found in the file workspaces /your workspace .metadata /.log file. Now we are focusing on JFace. JFace is a UI toolkit with classes for handling many common UI programming tasks. JFace is a Windows system independent in both its API and implementation, and is designed to work with SWT without hiding it. JFace includes the visual UI toolkit components of image and font registries, text, dialog, preference, and wizard frameworks, and progress reporting for long-running operations. Two of its more interesting features are actions and weavers. The action mechanism allows user commands to be defined independently from their exact whereabouts in the UI. Weavers are model-based adapters for certain SWT widgets, simplifying the presentation of application data structured as lists, tables, or trees. Here you can see JFace architecture. JFace establishes a layer between application's business logic and the bare bones SWT widgets. JFace uses methods like setText and setIcon to actually display data in widgets, and registers for low-level event as necessary. It also offers events to the application itself, but these are special in that they translate from the widget level to the model level. For instance, when a user selects a row in table widgets, SWT reports the index of the row. JFace translates that index into the model element, and it has previously rendered in the row and reports that this model element has been selected. In effect, the application is shielded from the cumbersome details and can always work in terms of its own data structures. In effect, of course, it still listens to the events such as button clicks directly on the SWT widgets, and translate this into operations in the model. JFace follows model view separation in getting data to be displayed from the model and listening to the change notification of the model to keep the display up to date. Here you can see SWT interacts with JFace. setText and setIcon are passed from JFace to SWT. Events are passed from SWT to JFace. JFace interacts with model get data is passed from JFace to model. Change is passed from model to JFace, and SWT is connected to listeners, and events are passed from SWT to listeners. JFace is connected to listeners. Model and view events are passed from JFace to listeners, and listeners are connected to model, and invoke operations are passed from listeners to model. Here you can see a bit more detailed JFace architecture. We will now discuss the various roles and relationships. Here we focus on viewers and their collaborations. The listeners, which implement the application reactions to user input in the sense of controllers. JFace viewers target specific widget types. The core contribution of JFace layer relates to its selection of generic viewers, each of which targets a specific type of widgets. A table viewer targets tables. A combo viewer targets a combo box, and so on. Viewers use the widget specific methods for displaying data and listen for widget specific events. JFace viewers access the application data through adapters. One question not addressed is how JFace will actually access the application specific data. How is a generic viewer supposed to know the right get data method and the implementation of observer pattern of specific data structures? First, each viewer holds a reference to the model in its property input. However, that input is a generic object, so the viewer never accesses the model itself. Instead, the viewer is parameterized by two adapter objects that enable it to inspect the model just as required. The content provider is responsible for traversing the overall data structure and for splitting it up into elements for displaying purposes. For a table or list, it provides a linear sequence of elements for a tree-like display. It also accesses the child and parent-like links between the elements. Furthermore, content provider must observe the model and notify viewer about any changes that it receives. Label provider is called back for each element delivered by the content provider, usually to obtain concrete strings and icons to represent the element on the screen. A list viewer will request one text icon combination per element. A table viewer or tree viewer will request one combination of each column. The viewer will also observe the label provider to be notified about changes of the text and icons to be displayed. The text-related viewers, text viewer and source viewer deviate from this schema in that they expect an implementation of iDocument as their model. The document itself then includes a text-specific access operation without requiring a separate adapter. The framework includes a deliberate redundancy regarding changes in the model. When values change within a data element, then those may be translated for the viewer either by the content provider by calling the viewer's update method or by the label provider by firing change events. Each mechanism has its merits. On the one hand, the content provider observes the model anyway, so the label provider can often remain passive. On the other hand, some generic label providers, such as those used in data binding, may wish to avoid relying on a specific content provider. Here you can see widgets interacts with viewer. Set icon and set text are passed from viewer to widgets, and selection is passed from widget to viewer. Viewer interacts with content provider. Get elements are passed from viewer to content provider, and refresh is passed from content provider to viewer. Content provider interacts with model. Get data is passed from content provider to model, and change is passed from model to content provider. Viewer is connected to model, and input is passed from viewer to model. And widget is connected to listeners. Events are passed from widget to listeners. Viewer is connected to listeners. Model level events are passed from viewers to listeners. Viewer is connected to label provider. Get text, get icons are passed from viewer to label provider. Listeners are connected to model, and invoke operations are passed from listeners to model. As an example, we can consider this code. Here you can see a hello world extend application window, and this class has run method and control and create contents method. As an example 2, we can consider setting up an Eclipse project to use SWT and JFace. Step 1. Identify the required external jar files for JFace. Step 2. Create an Eclipse project called org.eclipse.swt that will have all the required SWT and JFace jar files on its build path, and configure the order and export tab of the build path to export these files. This project will supply the required jar files to any other Eclipse project that needs them. Step 3. On any new Java projects that need to use SWT or JFace, simply add the org.eclipse.swt project as a required project on the projects tab of the build path. As an error example, we can consider this entry org.eclipse.jface 4/2010 0810 10:37:22.148. Message: problems occurred when invoking code from plugin org.eclipse.jface stack 0 java.lang. Illegal argument exception at org.eclipse.jdt.internal.core.util.scan type signature util.java 2710. This error occurred in Eclipse Java EE IDE for web developers, build ID 2009-20-1017. As an SW2 example, now we are focusing on SWT. SWT is an open source widget toolkit for Java designed to provide efficient portable access to the user interface facilities of the operating systems on which it is implemented. The standard widget toolkit provides a common OS independent API for widgets and graphics implemented in a way that allows tight integration with the underlying native Windows system. The entire Eclipse platform UI and the tools that plug into it use SWT for presenting information to the user. Here you can see a demo application on Windows 10. As an example, we can consider this code segment. The following is the basic Hello World program using SWT. It shows a window shell and a label. Contrary to Swing, display class is necessary to access underlying operating system, and its resources must be explicitly disposed of when they are no longer used. As an example too, we can consider steps to import SWT library. Right click on Java project, click properties. Step 2, click Java build path, then libraries, then add variable, then configure variable. Step 3, click new, then type a new variable name SWT_lib in names field. Step 4, click file and browse to SWT library file. PS SWT library is located at Eclipse plugin folder. Its name usually formatted as org.eclipse.swin32.win32.x86 _version number.jar. Here you can see the step 2. Click Java build path, then libraries, then add variable, then configure variables. As an error example, we can consider this. An SWT error has occurred. You are recommended to exit the Workbench. Subsequent error may happen and may terminate the Workbench without warning. See the .log file for more details. Exception stack trace org.eclipse.swt.swt error. No more handles at org.eclipse.swt.swt.error swt.java 4517 at etc. Now we are focusing on help. The Eclipse platform help mechanism allows tools to define and contribute documentation to one or more online books. For example, a tool usually contributes help style documentation to a user guide and API documentation if it has any to separate programmer guide. Here you can see creating a book. Eclipse platform can display any number of books, tables of contents. Each table of contents contains a collection of topics these are books, and sometimes a higher level component or product team is responsible for weaving together the documentation and topics supplied by any number of component teams. As an example, we can consider this code for creating book, and this file is books.xml. Here a book is just a table of contents. In fact, we could make a book out of each of the 3 TOC files here. But we will treat them as sections of a larger book instead. The one remaining piece of work is to update our plugin XML to actually contribute the TOC files that we created. Start with updating the plugin.xml to contribute our book. The important thing here is to define the table of contents as primary. And next we contribute the section TOC files, and the important thing here is that primary is not set, so its default value false gets picked up. That's it. You are done. Now take your plugin and drop it into the platform's plugins directory, that Eclipse, and start Eclipse and choose help, then help contents. Once you select the online help sample, then and expand the topics, you will see following. And as a small brief recap, we started by creating our plugin and document files. Next, we created TOC files to describe the structure navigation of our content. Then we then created the TOC file for the book and linked the other TOC files as sections of the book. Finally, we contributed all the files in the plugin.xml in the org.eclipse.help.toc extension point. Now we are focusing on Workspace. The various tools plugged into the Eclipse platform operate on regular files in the user's workspace. The workspace consists of one or more top-level projects where each project maps to a corresponding user-specified directory in the file system. The different projects in a workspace may map to different file system directories or drives, although by default all projects map to sibling subdirectories of a single workspace directory. Here you can see select a workspace dialog. As an example, we can consider this code segment. iWorkspace workspace equal resources plugin.get workspace. Interface iWorkspace. Workspaces are the basis for Eclipse platform resource management. There is only one workspace per running platform. All resources exist in the context of this workspace. iWorkspace is in package org.eclipse.core.resources. As an exception example, we can consider co-exception. If the method fails to copy some resources, the status contained in the exception may be multi-status, indicating where the individual failures occurred. Here we consider the exception which can occur in public iStatus copy iResources resources iPath destination boolean force iProgress monitor method in interface iWorkspace. And as an example too, we can consider workspace preferences. You can access workspace preferences from Eclipse menu, then window, then preferences. As an example, we can consider this situation in Eclipse Oxygen. Eclipse Oxygen stuck loading workspace. Now we are focusing on team. The team component is responsible for providing repository tooling integration into Eclipse and a universal compare facility for use by repository tooling and others. The Eclipse platform allows a project in the workspace to be placed under version and configuration management with an associated team repository. The platform has extension points and a repository provider API that allow new kinds of team repositories to be plugged in. Here you can see in M4, Java implements a team-aware content provider which allows the effects of an update to be shown with respect to the Java model. API has been added in M4 that allows models to provide a team-aware content provider that can be used by team providers to display the effect of a team operation in terms of model elements and hierarchies. The CVS team then update context menu action in Eclipse 3.2 milestone for M4 can be configured to display logical model elements and hierarchies, then previewing the effects of an update. You must run the perform client side merges on update preference on the team, then CVS, then work in progress preference page. There are 3 steps required to create a team aware content provider. Step 1, create extension to the org.eclipse.ui.navigator content extension point. Minimally, you will need to provide the content provider and label provider and an enablement rule that matches the appropriate model elements. The enablement rule should also match both iResource mapping scope and iSynchronization context, as either of these could be used as an input object to a team viewer. Step 2, associate your navigator content extension with the team viewer using the org.eclipse.ui.navigator.viewer extension point. The team viewer ID is org.eclipse.team.ui.navigator viewer. Step 3, bind your context extension to your model provider using the org.eclipse.theme.ui.theme content providers extension point. As an example, we can consider theme class. The theme class provides a global point of reference for the global ignore set and the text binary registry. The theme class is in org.eclipse.theme.co package. As an exception example, we can consider theme exception class. This exception is thrown by the theme provider API. It represents a failure in an API call. Since some API calls take multiple arguments, the exception is capable of returning multiple statuses. The API definition determines if the exception represents a single or multiple status response. This can also be tested on the exception instance itself. And theme exception class is in org.eclipse.theme.co package. Here we are considering identifying yourself. You can always change the information using GIT configuration. Click window, then preferences, then theme, then GIT, then configuration. Then next step, click new entry and enter the key value pairs, email, user.email and user.name. Here you can see user.email key value pair. Here Eclipse theme provider is EGIT. As another example, we can consider this. This is occurred under TFS Anywhere plugin on starting Eclipse, connecting an internal error occurred during connecting to Theme Foundation server, and an internal error occurred during connecting to Theme Foundation server com/microsoft/tfs/client/eclipse/project/project repository manager $ project repository data. Now we are focusing on platform runtime. A plugin is the smallest unit in Eclipse platform function that can be developed and delivered separately. Usually a small tool is written as a single plugin, whereas a complex tool has its functionality split across several plugins. Except for a small kernel known as platform runtime, all of the Eclipse platform functionality is located in plugins. As an example, we can consider platform class. The central class of the Eclipse platform runtime. This class cannot be instantiated or subclassed by clients. All functionality is provided by statics methods. Features include the platform registry of installed plugins, the platform adapter manager, the platform log, the authorization info management, this class is in the package org.eclipse.co.runtime. As an exception example, we can consider co-exception. If there are problems setting the authorization information, reasons include the keyring could not be saved. This exception can occur in method public static void add authorization info URL serve URL string realm string auth scheme map info in class platform. Here you can see clone the platform UI repository. To clone, select file, then import, then git, then project from git, then clone URI. Enter the URI from the Gerrit web page. Here in the first line of the wizard, the Eclipse GIT tooling removes the GIT clone from the clone URI automatically. And note that the URI automatically include your username. This make it easier to push the changes to the Eclipse Gerrit review system. If you clone the repository using the Eclipse GIT functionality, your local repository is already configured to push the changes to Gerrit. No additional setup step is required. This screenshot shows the selection. Please the depicted username with yours. On the next wizard page, you can select the clone all branches. The Eclipse platform project, the project uses the master branch for all bug fixes and feature works. Individual bug fixes are downported to maintainers branches, but you should always first fix the issue in the master branch. Finish this wizard by selecting next button until the option finish option becomes available. You end up with the projects from the repository imported into a workspace. You can also clone anonymously via anonymous HTTP, but if you just want to play with the source code locally and do not intend to contribute changes, in case you clone the GIT repository without using the Gerrit URL or not via Eclipse GIT, you have to adjust your push URL to provide Gerrit change. As an error example, we can consider this one: error log view missing by default on Eclipse platform runtime. This occurred in version 4.10 and under hardware PC Windows 10. Now we are focusing on a new tool. The platform also provides useful building blocks and frameworks that facilitate developing new tools. As an example, you can consider this. This is in plugin.xml. Plugin.xml defined extensions that this plugin provides extension points are how Eclipse advertises the plugin extensions. Much like USB Hub provides a generic connector that allows many other types of devices to be plugged in. The Eclipse extension points are documented in the help system, and each has a point identifier with optional children that are point specific. In this case, the extension is defined using the org.eclipse.ui.views point, which expect a combination of category and view elements. So this will look like this here. The class in this case extends the viewPart abstract class, which is used for all views in Eclipse 3.x. The Eclipse 4 model defines views in a different way. And Eclipse 4.x SDK include the 3.x compatibility layer, so this example will work in Eclipse 4.x SDKs. Here we can consider drawing a custom view. For the extension in plugins, an SWT canvas can be used to provide custom rendering for a view. As a starting point for drawing the clock, the canvas will use draw arc to create a circle. And step 1, remove the content of clock view, leaving behind an empty implementation of the set focus, and create part control methods. Then step 2, run the target Eclipse instance and see that clock view is now empty. Step 3, in the create partition control method, do the following. Step 1, create new canvas. Step 2, add paint listener to canvas. And step 3, get GC from paint event. And call draw arc to draw a circle. So code will look like this. And run the Eclipse instance and show the clock view. Then resize the view, and clock should change size with it. Here we can, as an example too, here we consider how to open plugins in Eclipse. Plugins for the open source IDE Eclipse let you use pre-built function in your own development projects. You can download plugins from the internet or create your own for later use. To open plugins in your Eclipse project, you import them into the project from their location on your hard drive or an Eclipse platform. Here step 1, click the file menu, select import. Step 2, click plugin development and plugins. Step 3, click the radio button under import from and choose which option you want, the current platform, a different platform, or your hard drive. Step 5, click the plugins you want to open to select them. Step 4, step 5, select an option under import as and determine what from the plugin should have. Click OK. As an error example, we can consider this plugin load error. java.lang.nullPointException. This is end of my presentation. Thank you very much for watching it.